Hello, hello, hello. Hey, that works. Good to see. Let's pop out chat. Go to YouTube. Sorry, I tried running OBS and it didn't work. Haven't updated since the last time. I had to update now. I thought Flatpak was supposed to ensure that it just kind of worked. I don't see what package exactly could have messed with that, honestly. Hey, Sorbet. Again, sorry for the delay. No, we got out quickly enough. Glad to see you again, though. I'm glad to finally be getting into traits. Excited to see it. Sorry, just a moment. Getting the chat for YouTube up in case we get some randos in. Would be good to see. Oh, that's fine. That's good. All right. All right. Really, I don't see any reason not to just start out. You're not going to be able to see me. Well, I really don't know what's happened since last time, but my face is gone. Popping in and out. Oh, that's why. We can see me much better. Got a privacy filter up here that wasn't working. Well, that's really good. It was a T thing. Right, I'm just going to start out. Glad to see you here, Sorbet. Traits and shared behaviors. Trait defines functionality a particular type has and share with other types. We can use traits to define shared behavior in an abstract way. We can use trait bounds to specify that a generic type can be any type that has certain behavior. He is the best string, seriously. I don't know why people sleep on it. Note, traits are similar to a feature often called interfaces in other languages, although with some differences. Defining a trait. A type's behavior consists of the methods we can call on that type. Different types share the same behavior if we can call the same methods on all of those types. Trait definitions are a way to group method signatures together to define a set of behaviors necessary to accomplish some purpose. For example, let's say we have multiple structs that hold various kinds and amounts of text. A news article struct that holds a news story filed in a particular location, and a tweet that can have at most 280 characters, along with metadata that indicates whether it was a new tweet, retweet, or reply to another tweet. I don't think they're called tweets anymore. We want to make a media alligator? Yeah, we want to make a media alligator. Fantastic. Aggregator library crate named Aggregator that can display summaries of data that can be stored in a news article or tweet instance. To do this, we need a summary from each type, and we'll request that summary by calling a summarize method on an instance. Listing 10-12 shows the definition of a public summary trait that expresses this behavior. We got a public trait, summary, which has a function in it, summarize, which takes in itself and outputs a string. A summary trait that consists of the behavior provided by a summarize method. Here, we declare a trait using the trait keyword and the trait's name, summary, capitalized in this case. We've also declared that the trait is public, so that crates depending on this trait can make use of this trait too. As we'll see in a few examples, inside the curly brackets, we declare a method signature that describes the behavior of the type that implements this trait, which in this case is summarize, taking a reference to itself, outputting a string. After the method signature, Instead of providing an implementation within the curly brackets, we use a semicolon. Each type implementing this trait must provide its own custom behavior to the body of the method. The compiler will enforce that any type that has the summary trait will have the method summarized, defined with this signature exactly. Okay, so this is just setting up like what we understand. What we are going to want from a function that implements this trait, like a display trait would probably output a string which can be displayed to the user, taking in only itself. So this is just okay, a general behavior which anything can implement. So even if a person made some function that can take out anything that has the summarize function, as long as it outputs a string, anything utilizing something with the summarize trait should be able to work with whatever output comes in, no matter what it is. Maybe? I don't think that was well explained, sorry. A trait can have multiple methods in its body. The method signatures are listed one per line. Each line ends in a semicolon. Implementing a trait on a type. Now that we've defined the desired signatures of the summary traits method, we can implement it on the types in our media aggregator. Listing 10-13 shows an implementation of the summary trait on the news article struct that uses the headline, the author, and the location to create the return value of summarize. For the tweet struct, we define summarize as the username followed by the entire text of the tweet. Assuming that tweet content is already limited to 280 characters. Alright, we're seeing it right here. We got a public struct news article with all of the individual pieces of it. We got implementing summary for news article. Function summarize just takes in itself, the summary, then outputs the entirety of headline. No, here we go. Yeah, it just takes in those pieces, headline, location, author, and places it here. Or, well, actually, no, it doesn't use content at all. Tweet. Yep, structure of tweet. Function summarize, taking in and returning the same thing. Puts in username and the entirety of the content formatted here. Implementing a trait on a type is similar to implementing regular methods. The difference is that after impl, we put the trait name we want to implement, then use the for keyword, and then specify the name of the type we want to implement the trait for. Let's look back at this, implementing summary for news article. Okay. And specify the name of the type we want to implement the trait for. Within the implement block, we put the method signature that the trait definition has defined. Instead of adding a semicolon after each signature, we use curly braces. Yeah. And fill in the method body with the specific behavior that we want the method of the trait to have for the particular type. Now that the library has implemented the summary trait on news article and tweet, users of the trait can call the method signature on instances of news article and tweet in the same way we can call regular methods. The only difference is that the user must bring the trait into scope, as well as the types. Here's an example of how a binary trait could use our aggregator library code, or library crate. We bring in aggregator, we bring in both summary and text. We let tweet equal some content, then we use print line to print the summary here. Okay. This code prints one new tweet. Of course, ebooks. Of course, as you probably already know, people. Okay. Other crates that depend on the aggregator crate can also bring the summary trait into scope to implement summary on their own types. One restriction to note is that we can implement a trait on a type only if at least one of the trait or the type is local to our crate. Sorry. One restriction is that we can implement a trait on a type only if at least one of the trait or type is local to our crate. Oh, okay, so we can only implement it if there exists one within our crate. What? For example, we can implement standard library traits like display on a custom type like tweet as part of our aggregator crate functionality, because the type tweet is local to our aggregator crate. We can also implement summary on vect in our aggregator crate, because the trait summary is local to our aggregator crate. Okay, however, I'm guessing when using it here, we're not allowed to, so we couldn't create a new implementation of summary inside of this code. Is that what it's saying? I guess that is, but we can't implement external traits on external types. For example, we can't implement the display trait on vec within our aggregator crate, because display and vect are both defined in the standard library and aren't local to our aggregator crate. This restriction is part of the property called coherence, and more specifically, the orphan rule, so named because the parent type is not present. The rule ensures that other people's code can't break your code, and vice versa. Without the rule, two crates can implement the same trait for the same type, and Rust wouldn't know which implementation to use. So if they did eventually update vect and add in the display trait, it wouldn't know what you're doing. Alright. Default implementations. Would that be an issue? I don't know if vec actually has a display. I can see a way that they could do that. Default implementations. Sometimes it's useful to have default behavior for some or all of the methods in a trait instead of requiring implementations for all methods on every type. Then, as we implement the trait on a particular type, we can keep or override each method's default behavior. In listing 10.14, we specify a default string for the summarize method of the summary trait instead of only defining the method signature, as we did in listing 10-12. Right, we've got public trait summary, taking in a string. Right, string from read more. That is the default output. To use a default implementation to summarize instances of news article, we specify an empty impl block with impl summary for news article. Right, yeah, so. Okay, yeah, I see. So, if we just want to use a default, which is defined inside of the aggregator part, I believe. I don't know where this would be specified. Source lib.rs. Yeah, this would be in the aggregator library. If we just want to use the default implementation, we can just have it be empty brackets instead. Yep. Even though we're no longer defining the summarize method on news article directly, we've provided a default implementation and specified that news article implements the summary trait. As a result, we can still call the summarize method on an instance of news article like this. News article, new article available. Article, not summarize. That'll output read more. New article available, read more. Creating a default implementation doesn't require us to change anything about the implementation of summary on tweet in listing 10-13. The reason is that the syntax for overriding a default implementation is the same as the syntax for implementing a trait method that doesn't have a default implementation. Okay. Default implementations can call other methods in the same trait, even if those other methods don't have a default implementation. In this way, a trait can provide a lot of useful functionality and only require implementers to specify a small part of it. For example, you could define the summary trait and have a summarize author summarize _ author method whose implementation is required, and then define a summarize method that is a default implementation that calls the summarize author method. Okay, so we have summarize author, which has itself and an output string, but we do have a default here. To use this version of summary, we only need to define summarize author when we implement the trait on a type. So implement summary for tweet function summary author, summarize author. Takes in self, returns a string. We are formatting, just taking self.username, formatting it with an @ ampersand. Well, I don't understand what that does, but hey. Then we output that as a string. After we define summarize author, we can call summarize on an instance of the tweet strip. And the default implementation of summarize will call the definition of summarize author that we've provided. Because we've implemented summarize author, the summary trait has given us the behavior of summarize method without requiring us to write any more code. Alright, one new tweet. That'll output read more from @horse ebooks. Oh, the ad is just, that's an actual piece of text. Yeah. Yeah, I got that eventually. Thank you for correcting me. Right. Note that it isn't possible to call the define default implementation on an overriding implementation of that same method. Alright, let's start this quiz. I'm not excited. I can't think today. Thoughts exit my head very quickly. Determine whether the method will pass a compiler. If it passes, give us the output. We got a trait, make noise. Function, make noise, brings in self with the default implementation of silent. We have a struct called dog, struct called cat, and implement make noise for dog. We overwrite the default with function make noise, fork. Sorry, I was going to make a joke. No, I stuck it. Here we go. That's better. Now it'll pass. Implement make noise for cat, brings in the default, silence. Right, let dog equal dog, a cat equal cat. Right, so we got a default implementation for dog and cat. Sorry, a default struct of dog and cat. Dog.make noise will print out bork. I don't think I see any issue here. Make noise for dog, function make noise at self, print bork. I see no reason why this doesn't work. I think it will compile. Silence and bork. Silence and bork. I guess they're looking for bark. Cowards. Alright. Yeah, every time I don't see issues, it makes me think that there's obvious issues I'm missing. But I think this is that simple. The following are statements about what kinds of trait implementations are permitted by Rust. Select each statement which is true. You can implement an external trait for a local type. Yes? I believe so. You can implement a local trait for a local type. Yes. You can implement a local trait for an external type. Yes. You can implement an external trait for an external type. No. I believe that the thing is that you gotta be one of these three need to be local. So either the trait or the type has to be local. Alright? What? It does compile, but apparently one of these is wrong. What? Oh my god, I got the order wrong. I'm an idiot. I told you. Yeah, I feel bad about that. I'm sorry, I failed you all. Right, so we got 1 out of 2. Well, I got 1 out of 2. I assume you got 2 out of 2 because, oh god, you can't be as dumb as I am today. Alright. Let's read this, though. The orphan rule requires that you cannot implement an external trait for an external type. I'm glad my failure brings you humor, Sorbet. To ensure code doesn't break if two traits provide conflicting implementations. Traits as parameters. Oh wait, would that bubble up? Oh, okay. I see the issue now. That'll bubble up. So if I implement display on vector, and then somebody else implements display on vector, you got two implementations, and one may override the other at a different point. Okay, I see why. I can see why now. Traits as parameters. Oh, okay, that's kind of funky. Oh, it needs an item that implements summary. Okay. So I could pass something in here that needs implement display. That's probably how the print line macro works. That's almost certainly how the print line macro works. Or at the very least, part of it. Now that you know how to define and implement traits, we can explore how to use traits to define functions that accept many different types. We'll use the summary trait. It is really cool. I think this is cool. We'll use the summary trait we implemented on the news article and tweet types in listing 10-13 to define a notify function that calls the summarize method on its item parameter, which is of some type that implements the summary trait. To do this, we use the infiltrate syntax, like this. Oh, so a reference to an item that I don't know what that means. An item that reference implements? Why is it referenced? Maybe it'll explain. Instead of a concrete type for this item, oh yeah, I get it. A reference and it implements summary. So instead of a concrete type for the item parameter, we specify the impl keyword and the trait name. This parameter accepts any type that implements the specified trait. I don't know why I didn't get that right away, but yeah. This will take up any type that has summary, and the reason why that can work is because summary always has to return a singular type, which is string. So no matter what, a string will be output by item if item is used with the summary. I wonder if it forces you to only use the summary method if you do this. Because if it's a different type, like if it's a number or something, and you try and do math on it, but then you bring in a string, that's not going to work. Would that be a runtime error, or would that not compile? This parameter accepts any type that implements a specified trait. In the body of notify, we can call any methods on item that come from the summary trait, such as summarize. We can call notify and pass in any instance of news article or tweet. Code that calls the function and any other type, such as a string or an I32, will compile because those types don't implement summary, and we can't implement them. Trait bound syntax. The infiltrate syntax works for straightforward cases, but is actually syntactical sugar for a longer form known as the trait bound. It looks like this. Okay. To be honest, I kind of prefer this. Right, so it's just an arrow brackets, any type that implements summary, and item of any type, or a reference to any type. This longer form is equivalent to the example in the previous section, but is more verbose. We place trait bounds with the declaration of the generic type parameter after a colon, and inside the angle bracket. Okay, I wonder if this gives you more freedom or something. I can't think of any different usage specific to this syntax, but I am curious. The infiltrate syntax is convenient and makes for more concise code in simple cases, while the full trait bound syntax can express more complexity in other cases. Oh, I see. I was right. For example, we have two parameters that implement summary. Can T have several traits? T is just a generic type. But are you asking if we can ask it if it implements multiple traits? I wonder, yeah, could we have like colon, could we have like, oh yeah, could we have like summary colon display colon something else? That's a good question. The impl syntax is convenient, makes more concise, but with fuller trait bounds. Syntax can express more complexity in other cases. For example, we can have two parameters that implement summary. Doing so with the impl trait, syntax looks like this, right? Here we just do it twice. I really hope they talk about that. Using impl trait is appropriate if we want this function to allow item 1 and item 2 to have different types, as long as both types implement summary. If we want to force both parameters to have the same type, however, we must use a trait bound, like this. Okay, so if we want everything within here to implement summary, we can do it as such. Item 1 of generic type T, which implements summary. Could we have like colon L, comma L colon display, and then have like this be at L, a different generic? The generic type T, specified as the type of the impl and item 2 parameters, constrains the function such that the concrete type of the value passed as an argument for item 1 and item 2 must be the same. Okay. Specifying multiple trait bounds with the plus. We can also specify more than one trait bound. Say we wanted notify to use display formatting as well as summarize on item. We can specify in the notify definition that item must implement both display and summary. Oh, that's what we were talking about. Okay, this is a bit of a weird syntax. Yeah, that is strange syntax, but that's what you're talking about, I believe. That is really strange syntax. I don't think without reading this I could ever understand what that was, even knowing what traits were. The plus syntax is also valid with trait bounds on generic types. Okay, here we go. That looks weird. With the two trait bounds specified, the body of notify can call summarize and use empty brackets to format items. Okay. I am glad that you can define multiple traits. That is something I was a bit worried about, and I'm glad that they brought it up here. Clearer trait bounds with where clauses. Oh, okay. Clearer trait bounds with where clauses. Using too many trait bounds has its downsides. Each generic has its own trait bounds, so functions with multiple generic type parameters contain a lot of trait bound information between the function's name and its parameter list, making the function signature hard to read. For this reason, Rust has alternative syntax for specifying trait bounds inside a where clause after the function signature. So instead of writing this, which would be some function inside here, we have T, which has display plus clone, U, which has clone and debug. I guess that is how you specify things with multiple types here. Alright. There's like 3 syntaxes for this. I hate that so much. Why are there like 3? There are 3 syntaxes for this. Why? Alright, so instead of putting it all here, inside of some function, right after it, we got all this trash, and then we got all this trash. You can't really understand what the thing is doing. Yeah, it's really poorly written here. I was thinking about that, like, clear trait bounds with where clauses. They should put this in bold or something to show that it was a keyword. Instead, they have it in just slightly lower, actually. This is anti-bolded. That's weird. I guess the entire title's bold and that's not bold, so it kind of sticks out, but I can completely understand not understanding that. I didn't at first either. Right, okay, so where syntax allows you to move this stuff down here, which is good. I like that. I like that it has this, but I really wish that they had just not had this. Why is this syntax still a thing that we're teaching at all? Two We have 3 different syntaxes for the same thing. I hate that so much. This function signature is less cluttered. The function name, parameter list, and return type are close together, similar to a function without lots of trait bounds. This is just going to get confusing. I'm going to get into a code base, and I'm going to forget that this type of syntax exists, or maybe another type of syntax in the 3, and then I'm just not going to know what I'm doing. I'm an idiot. I need things to be idiot-proof. Returning types that implement traits. We can also use the impl_trait syntax in the return position to return a value of some type that implements a trait, as shown here. Function return summarizable, implement summary. We can also use the implement return in the return position. What? I'm sorry, I don't understand. We can also use the impl_trait syntax in the return position to return a value of some type that implements a trait. Oh, I get it. So this is a function that will return any type that implements summarize. Okay. We have tweet, taking which has all of this stuff. Then we output it. So in a function like this, something that could be useful is just checking to see the length of like an input text. Like if you had return summarizable that took in some section of text, it could return either A, a tweet, or B, an article, depending on if it is able to be a tweet. So somebody could just write in their thoughts, and if it's able to be a tweet, it is a tweet. If it's not, it's an article. Okay, that's the use for that. By using impl summary for the return type, we specify that the returns summarizable function returns some type that implements the summary trait without naming the concrete type. In this case, returns summarizable returns a tweet, but the code calling this function doesn't need to know that. The ability to specify a return type only by the trait it implements is especially useful in the context of closures and iterators, which we'll cover soon. I believe that's in 2 different things? Yeah, we'll get that soon. I'm excited for that. Closures and iterators create types that only the compiler knows, or types that are very long to specify. The impl_trait syntax lets you concisely specify that a function returns some type that implements the iterator trait without needing to write out a very long type. I'd like to see what that type would look like. However, you can only use impl_trait if you're returning a singular type. For example, this code that returns either a news article or a tweet with the return type specified as impl summary will not work. Return is summarizable. We have ifs. Oh. You can only use impl_trait if you're returning a single type? So what I just said was impossible. Why? So it can't return either A news article, or B, a tweet. Why? Returning either a news article or a tweet isn't allowed due to restrictions around how the impl_trait syntax is implemented in the compiler. We'll cover how to write a function with this behavior in the using trait objects that allow for values of different types section of chapter 17. I guess we're not going to learn why for a very long time. Why? By using a trait bounds with an impl block that uses generic. I don't know what that was. I shouldn't have this up. Sorry. Why is it not going down? By using a trait bound with an impl block that uses generic type parameters, we can implement methods conditionally for types that implement the specified traits. For example, the type pair t in listing 1015 always implements the new function to return a new instance of pair t. Recall from the defining methods section of chapter 5 that self is a type alias for the type of the impl block, which in this case is pair of any type. But in the next impl block, pair T only implements the comp display method if its inner type T implements the partial OR trait that enables comparison and the display trait that enables printing. Did you follow that? I don't think I did. This is a run-on sentence. This is a massive run-on sentence. This entire paragraph is one sentence. Bruh? Yeah. If you're referencing, like, this massive thing. I don't know when you stated that, but I'm gonna have to read that again. I'm sorry, Sorbet. By using a trait bound with an impl block that uses generic type parameters, we can implement methods conditionally for types that implement the specified traits. Oh, it is two sentences. So basically, we can create a pair of two variables. For example, type pair T and listing always implements the new function to return a new instance of pair T. Recall from the defining method section of chapter 5 that self is a type alias for the type of the impl block, which in this case is pair T. But in the next impl block, pair T only implements the comp display method if its inner type T implements the partial order trait that enables comparison and the display trait that enables printing. Oh, okay. This pair implements the new function that helps create a new pair. Yeah. That's the new function. But it only, sorry, so new pair is on everything. But this only exists if it implements display and partial order. Is that all it's saying? You can then implement a function that makes sure that the new variable in a pair are able to be compared and displayed. Oh, okay. So, by my understanding, is comp display only going to exist if the pair can implement display and partial order, even though it may be any type? So since pair can be any type, comp display will only be implemented if the type of pair implements these two things, display and partial order. Oh, okay, yeah. Sorry, again, I'm not in the right mind today. Thank you for helping me out there. We can also conditionally implement a trait for any type that implements another trait. Implementations of a trait on any type that satisfies the trait bounds are called blanket implementations and are extensively used in the Rust standard library. For example, the standard library implements the toString trait on any type that implements the display. It's yeah, Rust is a strange beast. Any type that implements the display trait. The impl block in the standard library code looks similar to this code. Impl any type display toString for D. Because the standard okay, so this is just implementing toString for anything that has a display type. Sorry, anything that implements a trait display for any type. Okay. Oh, so anything that has, I don't know, man. Anything that has display will also have toString. Because the standard library has this blanket implementation, we can call the toString method defined by the toString trait on any type that implements the display trait. For example, we can turn integers into the corresponding string values like this, because integers implement display. Alright, so anytime we implement display, we will also be implementing toString. Makes sense, they're both just changing it into a string, and then displaying it. Well, either A, just transferring it to a string in order to be displayed, or in the toString method, transferring it to a string to be utilized in code. Blanket implementations appear in the documentation for the trait in the implementer section. Okay. So all blanket implementations appear there. Okay. I guess there's a lot of these. Traits and trait bounds let us write code that uses generic type parameters to reproduce duplications. But also specify to the compiler that we want the generic type to have particular behavior. The compiler then can use the trait bound information to check that all the concrete types used with our code provide the correct behavior. In dynamically typed language, we could get an error at runtime if we called a method on a type which didn't define the method. But Rust moves these errors to the compile time, so we're forced to fix all the problems before our code is even able to run. Additionally, we don't have to write code that checks for this behavior at runtime, because we've already checked at compile time. Think so improves performance? Sure does, without having to give up the flexibility of generics. I like that this does this. Determine whether it runs and what it'll execute. We have format display using this. Function, so we're bringing in display. Function displayable of any type that implements display. Taking in any type called T. And returns any type that implements display, and then just returns T. Or what was passed in. Right. Oh, this is a function. My god. Okay, the function takes in anything that implements T. Is that? Yeah, that's the syntax. That's fine. It takes in anything that implements T, and then outputs anything that implements display, and then it just returns whatever you pass in. I think that's fine. This isn't a reference, though, so does that mean it destroys itself? This isn't a reference T. That's no longer borrowing. That's just passing in a reference to the... unless it doesn't have copy. Right, so you have let s equal string from hello. We have let mutable s2 equal deployable s. Unless I'm wrong, I don't think that you can do this. You can't pass it in without it being a reference because it doesn't implement the copy trait. Right, so I'm just going to assume that's not an issue because I don't think that's what it's trying to tell us here. I just really don't understand ownership. The more I learn about it, the more I don't really understand what I'm doing. I really don't think that'll work though, so I am going to just say it does work for now. Right, s2.pushString base world, and print s2. I really don't think that'll work. We don't have ownership, do we? I finished the quiz. This one does not compile. Oh wow, you're way ahead of me. I am so sorry, Sorbet. Thank you for coming back to help me out. Yeah. I think that the issue here, just gonna guess, is that string doesn't implement the copy trait. Not about ownership? Okay, I'm not gonna get it then. Thank you again. What is the smallest set of trait bounds on T needed to make this function type check? Right. What is the smallest set of trait bounds on T needed to make this function type check? Right, so we have print T2, so we need display. We have clone. Right, clone and display. I think that's all we need. Yeah, I think that's all we need. 2 out of 2. All because of you. Because displayable returns impl display, then we only know that s2 is some type that implements display. Not that it is a string, which has a pushString method. Ah, yeah. Yeah, I see. I see. So this would work even if it didn't. mess with us, or even if it did compile, but we have to be really careful what we call on this. So this won't even compile. That was answering my question I had previously. What if we utilize a type in the incorrect way? Therefore, we cannot call s2.pushString if the return type of displayable was t. Then this program would compile. Really? Yeah, I don't see why not. What? Whatever. Alright, this does work. Context because clone was called, and the empty bracket display brackets are used as formatter, then t must be clone and display. Okay. You're probably halfway through this already. Thank you for sticking with me though, Sorbet. Validating references with lifetimes. Lifetimes is another kind of generic that we've already been using. Rather than ensuring that a type has the behavior we want. Yeah, because it would return a string for sure. Oh, yeah, I guess it would. Yeah, in that implementation, it would return a string for sure. You are correct about that, yeah. Again, sorry, very tired. Thank you for following along better than I. Lifetimes ensure that references are valid as long as we need them to be. One detail we discussed briefly in Chapter 4, permissions are returned at the end of a reference's lifetime, is that every reference in Rust has a lifetime, which is the scope for which that reference is valid. Most of the time, lifetimes are implicit and inferred. Just like most of the time, types are inferred. We only must annotate types when multiple types are possible. Annotate lifetimes when the lifetimes of reference objects could be related in a few different ways. Rust requires us to annotate the relationships using generic lifetime parameters to ensure the actual references used at runtime will definitely be valid. Annotating lifetimes is not even a concept most other programming languages have. So this is going to feel unfamiliar. Although we won't cover lifetimes in their entirety in this chapter, we'll discuss common ways you might encounter lifetime syntax, making it comfortable with the concept. Okay. Preventing dangling references with lifetimes. The main aim of lifetimes is to prevent dangling references, which cause a program to reference data other than the data it's intended to reference. Consider the unsafe program in listing 1016, which has an outer scope and an inner scope. Let R, let x equal 5, let R equal reference x. Reference x dies here, then we try and print R here. That is a use after free. Note, the examples in listing 1016, 1017, and 1023 declare variables without giving them an initial value. The variable name exists in the outer scope. At first glance, this might appear to be in conflict with Rust having no null values. However, if we try and use a variable before giving it a value, we'll get a compile time error, which shows that Rust indeed does not allow null values. It doesn't allow null values, but it does allow for naming before giving them a value, which is fine. That would be an undefined, I guess, which is nully in other languages. The outer scope declares a variable named R with no official value, and the inner scope declares a variable named X with the initial value of 5. Inside the inner scope, we attempt to set the value of R as a reference to X. Then the inner scope ends, and we attempt to print the value in R. If this code were executed, then undefined behavior would occur when R is read. However, this code would not compile because the value R is referring to has gone out of scope before we try to use it. Here is the error message. Right, we have X does not live long enough. Does anybody really live long enough? The variable X doesn't live long enough. The reason is that X will be out of scope when the inner scope ends on line 7. But R is still valid for the outer scope because its scope is larger. We say that it lives longer. If Rust allowed this code to work, R would be referencing memory that has been deallocated when X went out of scope. Anything we tried to do with R wouldn't work correctly. The borrow checker ensures data outlives its reference. The Rust... He died too young. Thoughts and prayers, my friends. The Rust compiler's borrow checker will compare scopes to determine whether all borrows are valid. Listing 1017 shows the same code as listing 1016, but with annotations showing the lifetimes of the variables. In comments. I don't know what this means, to be honest. And hitting lifetimes of R and X named A and B respectively. Oh, okay. So, I guess it's because this is too small. I can't see the A. Okay, so A lives here, and it lives until here. B lives here, dies here. Or, yeah, X. I don't know why they didn't just name it R and X. There's no reason not to. He had so much ahead of him, man. An entire print line. He never got to see the light of day. Here, we've annotated the lifetimes of R and A, of R with yes, and the lifetimes of X with B. As you can see, the inner B block is much smaller than the outer A lifetime block. At compile time, Rust compares the sizes of the two lifetimes and sees that R has a lifetime of A, but it refers to memory with a lifetime of B. The program is rejected because B is shorter than A. The subject of the reference doesn't live as long as the reference. Listing 1018 fixes the code so it doesn't have the dangling reference and compiles without any errors. Yep, just take it outside of that lifetime. The scope. A valid reference because the data has a longer lifetime than the reference. Here, X has the lifetime B, which in this case is larger than A, which means R can reference X because Rust knows that the reference R in R will always be valid while X is valid. Oh, maybe they're doing this because you can just like annotate X with like tilde B, and it'll just live for as long as R will live. Now that you know where the lifetimes of references are, and how Rust analyzes lifetimes to ensure references will always be valid, let's explore generic lifetimes of parameters and return values in the context of functions. Generic lifetimes and functions. We'll write a function that returns the longer of two string slices. This function will take two string slices and return a single string slice. After we've implemented the longest function, the code in 1019 should print the longest string is abcd. Let string 1 equal string from abcd, let string 2 equal xyz. The result, longest string 1 as string 2. Okay, yep, print line, the longest string is, passing back the result. Listing main function, yeah, we understand what that does. Note that we want the function to take string slices, which are references, rather than strings, because we don't want the longest function to take ownership of its parameters. Refer to the string slices as parameters section in chapter 4 for more discussion about why the parameters we use in listing 1019 are the ones we want. Okay. If we try to implement the longest function as shown in N20, it won't compile. We have X, which is a reference string, and Y, which is a reference string, returning a reference string. Then we just check which is longer, output the correct one. We don't know which one will be output though, so this won't work. Because I don't actually know. Instead, we get the following error that talks about lifetimes. Expected named lifetime parameter. Okay. There's more. This function's return type contains a borrowed value. The signature does not say whether it is borrowed from X or Y. Yep, so the issue really is that we don't... Oh, what is this? Longest within arrow brackets, A. That is the lifetime, I'm guessing. Yeah, it annotates it here. I think I may be right. It's annotating the lifetime here. Oh no, that's a suggestion. That is suggesting a generic lifetime. I see. The help text reveals that the return type needs a generic lifetime parameter on it because Rust can't tell whether the reference being returned refers to X or Y. Actually, we don't either, because the if block in the body of this function returns a reference to X, and the else block returns a reference to Y. When we're defining this function, we don't know the concrete values that will be passed into this function, so we don't know whether the if case or the else case will execute. We also don't know the concrete lifetimes of the reference that will be passed in, so we can't look at the scope, as we did in listing 1017 and 1018, to determine whether the reference we return will always be valid. The borrow checker can't determine this either, because it doesn't know how the lifetimes of X and Y relate to the lifetimes of the returned value. To fix this error, we'll add generic lifetime parameters that define the relationship between the references so the borrow checker can perform its analysis. Okay, so this is just ensuring that both of them will live the exact amount of time. Yeah, okay, I see. The main reason for this, I guess, just to go back to what we've had before, what if string 1 was in a different scope? We started scope blocks around here and ended them here. String 1 would still be alive, but string 2 would not be before the print line. So it would work if we use string 1, but not if we use string 2, because string 2 would be dead. Okay. Lifetime annotation syntax. Lifetime annotations don't change how long any of the references live. Rather, they describe the relationship of the lifetimes of multiple references to each other without affecting the lifetimes. Just as functions can accept any type when the signature specifies a generic type parameter, functions can accept references with any lifetime by specifying a generic lifetime parameter. Lifetime annotations have a slightly unusual syntax. The names of lifetime parameters must start with an apostrophe. I don't know why I said tilde before, that is an apostrophe. And are usually all lowercase, very short, like generic types. Most people use the name A for the first lifetime annotation. We'll place lifetime parameters annotations after the of a reference, using a space to separate the annotations from the references type. Here are some examples. A reference to an I32 without a lifetime parameter, 32 with a lifetime parameter named A, and an I32, and mutable I32 with a lifetime of A. We have a reference, I32. We just put the apostrophe A beforehand if we wanted to have a lifetime of A. Or we're just annotating the lifetime, I guess. One lifetime annotation by itself doesn't have much meaning, because the annotations are meant to tell Rust how generic lifetimes parameters of multiple references relate to each other. Let's examine how the lifetime annotations relate to each other in the context of the longest function. Lifetime annotations in function signatures. To use lifetime annotations in function signatures, we need to declare the generic lifetime patterns, or parameters, inside angle brackets between the function name and the parameter list, just as we did with generic type parameters. We want the signature to express the following constraints. The returned reference will be valid as long as both the parameters are valid. This is the relationship between lifetimes of the parameters and the return values. Name the lifetime apostrophe A, and then add it to each reference, as shown in listing 1021. Right, angle brackets has generic lifetime A, then we tell it A. All of them are generic lifetime A STRs, references to a string slice with a lifetime of A. This code should compile and produce the results we want when we use it with the main function listing 1019. The function signature now tells Rust that for some lifetime A, the function takes two parameters, both of which are string slices that live at least as long as lifetime A. The function signature also tells Rust that the string slice returned from the function will live at least as long as lifetime A. In practice, it means that the lifetime of the references returned by the longest function is the same as the smaller of the it it means that the lifetime of the reference returned by the longest function is the same as the smaller of the lifetimes of the values referred to by function argument. That is a poorly made sentence, but I think I understand that it means that no matter what lifetimes are passed in, both will last at the very least the smaller of the lifetimes. It means that the lifetime of the reference returned by the longest function is the same as the smaller. Okay, yeah. The lifetime will always be the smaller of the two. These relationships are what we want Rust to use when analyzing this code. Apologies again. I'm very tired. Remember, when we specify the lifetime parameters in this function signature, we are not changing the lifetimes of any value passed in or returned. Either, we're specifying that the borrow checker should reject any values that don't adhere to these constraints. Note that the longest function doesn't need to know exactly how long x and y will live, only that some scope can be substituted for lifetime A that will satisfy this signature. When annotating lifetimes of functions, the annotations go in the function signature, not in the body signature. Not in the function body. The lifetime annotations become part of the contract of the function, much like the types in the signature. Having function signatures contain the lifetime contract means the analysis the Rust compiler does can be simpler. If there's a problem with the way a function is annotated or the way it is called, the compiler errors can point to the part of the code that constrains more precisely. If instead the Rust compiler made more inferences about what we intend the relationship of the lifetimes to be, the compiler might only be able to point to a use of our code many steps away from the cause of the problem. When we pass concrete references to longest, the concrete lifetime that is substituted for lifetime A is the part of the scope of X that overlaps with the scope of Y. In other words, the generic lifetime A, will get the concrete lifetime that is equal to the smaller of the lifetimes of X and Y. Because we've annotated the return reference the same lifetime parameter, lifetime A, the return reference will also be valid for the length of the smaller of the lifetimes X and Y. Let's look at how the lifetime annotations restrict the longest function by passing in references that have different concrete lifetimes. Listing 1022 will be a straightforward example. Alright, so exactly what I suggested originally, we have string 1 and string 2. The string 2 will die at the end here. That'll work because, well, we do not use result at any point after string 2. However, if we tried to, it would fail. Because string 2 is alive. String 2 is dead, even though string 1 is alive. And this will work. Using the longest function with references to string values that have different concrete lifetimes. In this example, string 1 is valid until the end of the outer scope. String 2 is valid until the end of the inner scope. The result references something that is valid until the end of the inner scope. Run this code, and you'll see that the borrow checker approves. It will compile it and print the longest string is long, string is long. I didn't read this. That is horrible. Longest string is long, string is long. Next, let's try an example that shows the lifetime of the reference in result. It must be the smaller lifetime of the two arguments. We'll move the declaration of result variable outside the inner scope, but leave the assignment of the value outside the inner scope, but leave the assignment of the value to the result variable inside the scope with string 2. We'll move the declaration of the result variable outside the inner scope, but leave the assignment of the value of the result variable inside the scope with string 2. Okay, sure. I mean, I understand it, but it's poorly written. Then we'll move the print line that uses result to the inner scope. To outside the inner scope, sorry, putting it outside, right? So we're just moving print line outside of the inner scope, and it won't work because even though result originally had the full lifetime, when it is returned, result actually has the lifetime of string 2. I don't even think, if you put print line inside of here, I don't know if that would work. Does result's lifetime decrease, or does this not fail? Does this, you just followed. Wow, thank you. Sorry, that took me under. Thank you for that survey. That freaked me out just a little bit. Yeah. I really am curious what the error is going to be. When we try to compile this code, we get an error. String 2 does not live long enough. So it just directly points to string 2 being the problem. Okay. String 2 dropped here was still borrowed. I was shocked that I wasn't following you. No, that's perfectly fair. I wouldn't follow me either, to be honest. How do you get in every time? Do you just follow the link on Lemmy? Wow, I was thinking of stopping posting those. I'm glad I didn't. I'd miss you. Right, so drop here will still borrowed. Borrowed value does not live long enough. And it's saying that the issue is, well, yeah, when we push it into here as string. Borrow later used here, inside of the print line. Result. More information about the error, yep. Okay, I'm really curious if we put in the print line to here, would that fail? I don't think it would actually. The error shows that for result to be valid, the print line statement, string 2, would need to be valid until the end of the outer scope. Rust knows this because we annotated the lifetimes of the function parameters to return values using the same lifetime parameters for lifetime A. As humans, we can look at this code and see that string 1 is longer than string 2, and therefore result will contain a reference to string 1. Because string 1 has not gone out of scope yet, a reference to string 1 will still be valid for the print line statement. However, the compiler can't see that the reference is valid in this case. It would have to run the code. We've told Rust that the lifetime of the reference returned by the longest function is the same as the smaller of the lifetime of the reference. I'm sorry, I read that in weirdly. We've told Rust that the lifetime of the references returned by the longest function is the same as the smaller of the lifetimes of the references passed in. This is not just me being tired. This is terribly written. They need an editor to go through this. I know it's just like a college, but like they can get an editor to read through this stuff for clarity. Try designing more experiments that vary the values and lifetimes of the references passed in to the longest function and how the returned reference is used. Make hypotheses about whether or not your experiments will pass the borrow checker before you compile and check to see if you're right. I'm not going to do this. You can do this. I'm not going to do this. Either that or you're late. You usually get in stream until it starts. Oh, so you just come directly here. Wow. That is a good way to do it. I usually am late. Sorry about that. Survey. Which kind of programming error is a lifetime supposed to prevent? Starting this quiz. Indexing past the bounds of an array for overflow. Nope. Using the result of a fallible computation for checking for the possibility of an error. Using a reference to an object after its memory has been freed. That's it. Not allocating enough memory. It is use after free. Determine whether the program will pass the compiler. If it does, print it out, right? So we have an if function, right? So we got shortest, lifetime A, lifetime B. X is a reference to a string with lifetime A. Y is a reference to a string slice of lifetime B, returning a reference to a string slice lifetime a. Okay, so if x.length greater than y.length, no, this won't work. This won't work at all. This won't work because a and b are different lifetimes, and one could be shorter than the other. We don't know. No, we know which one has to be the longest. But what if it passes through b? Sorry, y. If it passes back y, it is not necessarily lifetime a. So no, this won't pass the compiler, but this is not a direct error that we've seen yet. Well, I mean, it kind of is, but you know. Nope, does not compile. Okay. A little bit of context here. Lifetimes help identify how long an object will live and whether references to that object outlive the object itself. A little bit of context here. If the type signature says that the function must return a reference to the lifetime a, then it would be invalid to return a reference with a different lifetime, like b. Thinking in terms of lifetimes. The way in which you need to specify lifetime parameters depends on what your function is doing. For example, if we change the implementation of the longest function to always return the first parameter, rather than the longest string slice, we wouldn't need to specify a lifetime on the y parameter. The following code will compile. Alright, we have x, lifetime a, and y, no lifetime specified. We always return something with a lifetime of a, and return x as a lifetime of a. We specified a lifetime parameter a for the parameter x and the return type, but not for the parameter y, because the lifetime of y does not have any relationship with the lifetime of x or the return value. Yep, this could be useful if y was used only within this function, but x or something derived from x would be the only thing that is passed back, or if we modify x in some way here. But in no way utilize y. When returning a reference from a function, the lifetime parameter for the return type needs to match the lifetime parameter for one of the parameters. If the reference returned does not refer to one of the parameters, it must refer to a value created within this function. However, this will be a dangling reference because a value will go out of scope at the end of this function. Consider this attempted implementation of the longest function that won't compile. Alright, yep, we bring in x, we bring in y, but the result will be a string from a really long string. So I can't get the this is funny, I like this. Get the longest between x and y, and you just say, hey, here is literally the longest string which you can put in Rust. This will always be longer than whatever you put in. Even though we specified a lifetime parameter of a for the return time, this implementation will fail to compile, because the returned value lifetime is not related to the lifetime of the parameters at all. Here's the error message we get. It returns a reference to data owned by the current function. Oh, okay. Oh, cannot return reference to a local variable result. Yep, because this will die. Could we give the result something with this lifetime? Problem is the result goes out of scope and gets cleaned up at the end of the longest function. We're also trying to return a reference to result from this function. There's no way we can specify lifetime parameters that would change the dangling reference. And Rust won't let us create a dangling reference. In this case, the best fix would be to return an owned data type rather than a reference to the calling function, so that the calling function is then responsible for cleaning up the data. Ultimately, lifetime syntax is about connecting the lifetimes of various parameters and return values of functions. Once they're connected, Rust has enough information to allow memory-safe operations and disallow operations that would create dangling pointers or otherwise violate memory safety. Lifetime annotations in struct definitions. So far, the structs we've defined all hold owned types. We can define structs to hold references, but in that case, we would need to add a lifetime annotation on every reference in the struct's definition. Listing in 1024 has a struct named important excerpt that holds a string slice. Yep. Okay, this does make sense because we could set one of the struct's values to something, to a reference that may live shorter or longer than another. Okay, so we have important excerpt part, a reference to a string with a lifetime of a, let novel string from here is the novel, first sentence equal novel split on a period, next expect, could not find a dot if it fails. Let I equal important excerpt part for a sentence. Yep. This struct has the single field part that holds a string slice, which is a reference. As with generic data types, we declare the name of the generic lifetime parameter inside angle brackets after the name of the struct, so that we can use the lifetime parameter in the body of the struct definition. This annotation means an instance of important excerpt can't outlive the reference it holds in its part field. The main function here creates an instance of the important excerpt struct that holds a reference to the first sentence of the string owned by the variable novel. The data in novel exists before the important excerpt instance is created. In addition, novel doesn't go out of scope until after the important excerpt goes out of scope. So the reference in the important excerpt instance is valid. Lifetime Elysian. What? I'll admit I've never seen what the word Elysian means. What is Elysian? The omission of a sound or syllable when speaking. Okay, you've learned that every reference has a lifetime, and that you need to specify lifetime parameters for function or structs that use references. However, in chapter 4, we had a function in listing 4.9, shown again in listing 10.25, that compiled without lifetime annotations. Right? We have S, which is a reference string, and S, which is a reference string, and in the end, we are returning S after modifying S. We are returning a reference to the same thing that this is implied black times, right? The reason this function compiles without lifetime annotations is historical. In early versions, pre 1.0 of Rust, this code wouldn't have compiled, because every reference needed an explicit lifetime. Okay? At that time, the function signature would have been written like this. The reason is because it is historical, and in the history it wouldn't work. In history that wouldn't work. What? After writing a lot of Rust code, the Rust team found that Rust programmers were entering the same lifetime annotations over and over in particular situations. These situations were predictable and followed a few deterministic patterns. The developers programmed these patterns into the compiler's code, so the border checker could infer the lifetimes in these situations and wouldn't need explicit annotation. This piece of Rust history is relevant. Another set of rules? Yeah. This piece of Rust history is relevant because it's possible that more deterministic patterns will emerge and be added to the compiler. In the future, even fewer lifetime annotations may be required. That is good. Sorry, I'm just complaining about syntax a lot here. I'm going to try and stop that. The patterns programmed into Rust's analysis of references are called the lifetime Elysian rule. Why? What is an Elysian? Have you ever heard the word Elysian? I'm going to have to assume. Process of joining together or merging things, especially abstract ideas, is a secondary thing. What are we merging together? I'm sorry. Have you ever heard the word Elysian? I've never. This is some... whatever. Programmers terrible at naming things. These aren't rules for programmers to follow. They're a set of particular cases that the compiler will consider. And if your code fits these cases, you don't need to write the lifetimes explicitly. Well, in this case, that is what lifetime Elysian means, yeah. The Elysian rules don't provide full inferences. Don't provide full inference. If Rust deterministically applies the rules, but there is still ambiguity as to what lifetimes the references have, the compiler won't guess what the lifetime of the remaining references should be. Instead of guessing, the compiler will give you an error that you can resolve by adding the lifetimes annotations. Right, so I guess what this is really telling us is that we have an incomplete set of inferred lifetimes. There are many inferred lifetimes, however, it is incomplete, and eventually it will become more and more complete. That's really what it's saying. Lifetimes on functions or method parameters are called input lifetime. Input lifetimes and return variables are called output lifetime. The compiler uses 3 rules to figure out the lifetimes of the references when there aren't explicit annotations. The first rule applies to input lifetimes, and the second and third rules apply to output lifetimes. If the compiler gets to the end of the 3 rules and there are still references for which it can't figure out lifetimes, the compiler will stop with an error. These rules apply to function definitions as well as input blocks. The first rule is that the compiler assigns a different lifetime parameter to each lifetime in each input type. References like ampersand lifetime underscore I32 needs a lifetime parameter. And structures like important events needs a lifetime parameter. But I really don't know what it's saying here. I guess this is saying that it wasn't given originally, so it needs to add a new one, which is different than this one. For example, function foo x reference I32 would get one lifetime parameter and becoming function foo lifetime a x reference to an I32 with lifetime a. The function with 2 parameters would get 2 different lifetimes, so on and so forth. Or I guess the function would get 2 lifetime parameters and become function foo a b with x. What? I don't understand this one. Of type reference important to excerpt, I'm guessing that's a struct. The second rule is that if there is exactly one lifetime... Oh, that's an enumeration? I don't know what I'm talking about here. The second rule is that if there is exactly one input lifetime parameter, that lifetime parameter is that lifetime is assigned to all output lifetime parameters. Function foo lifetime a x lifetime a I32 reference outputs lifetime a reference to an I32. The rule is if there are multiple, I think these rules are what the compiler does to check if a reference needs a lifetime. Yeah, this is what the compiler does to ensure that the lifetimes are there and infer the lifetime. These 3 rules are just that. Just to check if you need to specify a lifetime yourself. If it passes all 3 of them, then it's fine. If it doesn't, then it's going to pass back to you with an error. I just really don't understand what this is doing here. Sorry, I'm not able to describe correctly what I'm thinking or saying. The third rule is if there are multiple input lifetime parameters, but one of them is self or immutable self, because this is a method, the lifetime of self is assigned to all output lifetime parameters. This third rule makes methods much nicer to read and write because fewer symbols are necessary. Oh, okay, yeah. Okay. Oh, X, which implements. Oh, okay. I think the trait important excerpt. Whatever. Let's pretend we're the compiler. We'll apply these rules to figure out the lifetimes of the references in the signature of first word function in 1025. The signature starts without any lifetimes associated with the reference. We have function first, s, string, string, right? Let's do this without it first. So we would have, oh, no, it's not. It's just going to say it here, and I mean, come on. Then the compiler applies the first rule, which specifies that each parameter gets its own lifetime. We'll call it, the first rule is that the compiler assigns automatically a lifetime reference to inputs and outputs, default lifetimes. Yep. And it applies a different lifetime to every single one, a different generic lifetime to all of these things, input, output, and every single parameter. I believe. Let's just double check. Oh, well, that's not output. That's not output. There's no output here. But yeah. Right. So here we would just have a lifetime A, which adds on here, and string has no lifetime. The reference string has, well, it would be the lifetime of the original. The second rule applies because there is exactly one input lifetime. The second rule specifies that the lifetime of the one input parameter gets assigned to the output lifetime. So the signature is now this. Oh, yeah, this is step by step. This is the same lifetime. Now, all the references in this function signature have lifetimes, and the compiler can continue its analysis without needing the programmer to annotate the lifetimes in this function signature. Let's look at another example, this time using the longest function that had no lifetime parameters when we started working with it in listing 1012. Alright, we have x and y, which each get their own lifetimes a and b. And this, well, we'll see. It doesn't know. Let's apply the first rule. Each parameter gets its own lifetime. This time we have two parameters instead of one. So we have two lifetimes, A and B. We add it on here and here. This does not yet have it. You can see that the second rule doesn't apply because there is more than one input lifetime. The third rule doesn't apply either because longest is a function rather than a method. So none of the parameters are self. After working through all three rules, we still haven't figured out what the return type's lifetime is. Oh, okay, yeah. Yeah, the third rule is just like for self, I guess. We still haven't figured out what the return lifetime is. This is why we got an error trying to compile the code in listing 1020. The compiler worked through the lifetime deletion rules, but still couldn't figure out all the lifetimes of the references in its signature. Okay, yeah. Alright, so rule 1 is give the parameters a lifetime. Give every parameter a separate lifetime. Rule 2 is if there is only one parameter, you can give the return type the same parameter, or the same lifetime. Third rule is if one of the parameters are self, it has the lifetime of the function itself. Or it has the same lifetime as the original thing. Alright, and if at the end all pieces of the signature aren't annotated with a lifetime, it will error out. Lifetime annotations in method definitions. When we implement methods on a struct with lifetimes, we use the same syntax as that of generic type parameters shown in listing 1011. Where we declare and use the lifetime parameters depends on whether they're related to the struct field or the method parameters and return values. Lifetime names for struct fields always need to be declared after the impl keyword, and then used after the struct's name. Oh, hey, Shafi, welcome in. Just gonna quickly describe, we are learning Rust for usage in the Lemmy application. I'm glad to see you here. This is the first time we've had a new guy, but we're just learning how to code. We're currently on chapter 10, I believe. You're free to come in and just listen in. Maybe you'll learn something new. I'm not learning much. I'm quite tired. But if you go to Twitch, we are currently learning for this program called Lemmy. It's like Reddit, but not owned by anybody. Again, glad to see you in here, but I am going to continue along. Right. Lifetimes names for struct fields always need to be declared after the impl keyword and then used after the struct's name, because those lifetimes are part of the struct's types. In method signatures inside of the impl block, references might be tied to the lifetimes Fair enough, Shafi. To the reference lifetime or references in the struct's field, or they might be independent. In addition, the lifetime's elision rule often makes it so lifetime annotations aren't necessary in the method signatures. Let's look at some examples using the struct named important excerpt that we defined in listing 1024. It's 1:33 a.m. here? Where are you? You must be Central Europe? Africa? That would probably be like Germany-ish? Where exactly are you? I'm really curious now. Sorry, Survey. Oops, yeah, only inputs? Sorry, I missed that too. Germany. Yes, right. Glad to have you in here. First, we'll use the named method. First, we'll use the method named level. Wow. Great first introduction to myself, I assume. Whose only parameter is a reference to self, and whose return value is an I32, which is not a reference to anything. We have implemented lifetime A, important excerpt, with a type with the lifetime A, function, level, as self, Rust. Oh yeah, do not do Rust at 3 a.m. That is a danger. And it outputs an I32 of type, which is just the number 3. The lifetime parameter declaration after impl and its use after the type name are required, but we're not required to annotate the lifetime of the reference to self because of the first elision rule. I thought that was the third. Okay. Here's an example where the third lifetime elision rule applies. Implementing important excerpt with lifetime of A, function announce and return part, which has self, which takes in self, and announcement of type reference string, returning a reference to a string. We have print line, attention please, and then we have the announcement. Afterwards, to replace self.part, which is different than announcement, which is a reference string. There are 2 input lifetimes, so Rust applies the first lifetime elision rule and gives both self and announcement their own lifetimes. Then, because one of the parameters is self, the return type gets the lifetime of self, and all lifetimes have been accounted for. Oh, okay. That's good to hear. The static lifetime. One special lifetime we need to discuss is static. No, this is the Rust program. Oh, wow. Yeah, we've got 2 separate people coming in looking for Rust the video game. Maybe I should change my title? That is completely fair. Yeah. We lure you in with the idea of a very nice old game, and we forcibly teach you about lifetimes in the Rust programming language. So I guess you could program mods for Rust in the Rust programming language. Sorry, man. The static lifetime. One special lifetime we need to discuss is static, which denotes that the effective reference can live for the entire duration of the program. All string literals have the static lifetime, which we can annotate as follows. Let S of type reference string with a lifetime of static equal I have a static lifetime. The text of this string is stored directly in the program's binary, which is always available. Oh yeah, it's just a programming language. It's what lemmings written in. You know what? I'm gonna post you the website actually. Check it out if you like it. This is just one of many. I'm not allowed to chat here. Why am I not allowed to chat here? Ah, that's why. Okay. Check this out. I guess you'll have to type that in. Maybe because I have a slash? Ah, whatever. Put that into your browser. Shit just works. And shit just works. Again, it's Reddit, but made by random people instead of a big company. We don't steal your information. If I can do one good thing today, it'll be getting you off of that part of the internet. Thank you, Shafi. I'm very glad to have you if you do join. I'm sorry book broke on there. The text of the string is stored directly in the program's binary, which is always available. Therefore, the lifetime of all string literals is static. You might see suggestions to use the static lifetime in error messages, but before specifying static as the lifetime for a reference, think about whether the reference you have actually lives for the entire lifetime of your program or not, and whether you want it to. For most of the time, an error message suggesting the static lifetime results from attempting to create a dangling reference or a mismatch of the available lifetimes. In such cases, the solution is fixing those problems, not specifying the static lifetime. Alright, so what I'm hearing here is make everything static. Everything's in memory the entire time. Never let it leave my clutches. Generic type parameters create bounds and lifetimes together. Let's briefly look at the syntax of specifying generic type parameters. Create bounds and lifetimes all in one function. It's going to be quite long. Oh, the where is after this. I see. That's going to make this long, boy. Alright, so we have standard, format display, we have a function, longest with an announcement, has a lifetime of A, and a generic type. Has one singular lifetime of A, everything passed in will have to be of lifetime A. It worked without the slash. I'm glad to hear. Alright, we get X with a lifetime of A, which is a reference string. Same with Y. We have AND, which is any type, but has no lifetime specified. Alright, and we return a reference to a string with a lifetime of A. And could technically be a reference string, but we can't pass it back. I doubt we do. Right where P implements display. So it has to be a type that implements display, and X as well as Y have to have a lifetime that fit within each other, or a lifetime, sorry. The output will have to exist for a period of time equal to the smallest of Y and X's lifetimes. And inside the function, we have a print line, which prints and if the x.length, or if it's bigger, it gets passed back. The biggest of the two passed back. This is the longest function from listing 1021 that returns the longer of the two string slices. But now it has an extra parameter named an of the generic type T, which can be filled in by any type that implements the display trait as specified by the where clause. I'm sorry, but my head get a headache with so much information. Completely fair. We can only do this in 2-hour blocks, man. I completely understand. If you want to learn more, go back to the first section. You'll grow your brain to be able to withstand all this capacity, man. Thank you for joining us, though. You have been appreciated. Right. Which can be filled in with any type of, This extra parameter will be printed using, the default implementation. It'll be printed here. That is a weird thing to say. Which is why the display trait bound is necessary, because lifetimes are a type of generic. The declaration of the lifetime parameter, lifetime A, and the generic type parameter T go in the same list inside the angle brackets after the function name. Right, after this quiz and this summary, I think we're done for the day, but hey, let's start it up. Quiz time! If a reference has a lifetime static, this means the data under the reference lives in the static region of memory. Or, the data under the reference is never deallocated. Or, the data under the reference is not dynamic. Or, the data under the reference cannot be mutated. Okay, when I read originally, I thought this was not correct. I mean, it is deallocated by the operating system when the application is quit or forcibly closed. That is the correct answer. Consider the following unannotated function signature. Will Rust accept this function signature? If so, what lifetimes will it inherit? We have a struct foo with a lifetime A. We have bar, which has a lifetime A, which is a generic. Right, function baz, f foo, turning an I32. F of type foo, which I think this will work. I don't see why it wouldn't. Right, so here we will have baz, which is the lifetime of A, f, which is foo of a lifetime of A, returning an I32 with no lifetime. That is incorrect. I believe this is the most correct, maybe? What's the difference between here and here? What is the difference between here and here? Oh, no, this one's correct. Yep, there's a lifetime set towards foo. F will have the lifetime of A as well. And the return type will also have the same lifetime. I think that's correct. Could be wrong. Consider the following unidentified function signature. We have this. Well, is that not the same? What is the difference? I don't see a difference. I choose the one that has the most lifetimes. Honestly, yeah, I think that's safe. We have will Rust accept? Right, what's the problem here? Will Rust accept the signature? Right, we have foo. We have F, which is a reference to foo, and an I32. I don't think this one actually has them. Yeah, I guess what? Could a reference not have a longer lifetime? It would have to have the same. What? I really don't understand here. Right, so here we have A and B. We have foo, which has a lifetime of B. I think it'll reject because too many lifetimes. Yeah, because how does it know which one? I think this really gives it away that you're correct here. I think it'll reject too because it doesn't know what lifetime it's going to pass back. But both lifetimes are necessary. Yeah. I think that's why it'll reject, because of that issue. Yeah, you're entirely correct on that. Rust will reject this function signature. Hey! Completely correct. Thank you for steering me in the right direction there. Alright, let's read the context. Static means live for the entire program. And so data under a static reference must never be deallocated. In practice, static references are usually not mutable. The meaning of static, lifetime has no essential relationship with mutability. Question 2. Context. The struct takes a single lifetime parameter, and the output has a single lifetime. So Rust assumes they are the same. We are getting the quizzes correctly. Have we gotten them all correct? It's only because of you, really, honestly. I kind of wanted to go for the wrong direction some places. I thank you for steering me correctly. The struct takes a single lifetime parameter. Yep. Question 3. Rust will not compile this program because it is ambiguous whether the lifetime of the output is tied to the lifetime of foo or the reference foo.bar. Ah! Yep, we were completely correct. Well, that feels good. We covered a lot in this chapter. Now that you know about generic type parameters, traits, and trait bounds, and generic lifetime parameters, you're ready to write code without repetition that works in many different situations. Generic type parameters let you apply the code to different types, traits. Traits and trait bounds ensure that even though the types are generic, they'll have the behavior the code needs. We learned how to use lifetime annotations to ensure that this flexible code won't have any dangling references. And all of this analysis happens at compile time, which doesn't affect runtime performance. Believe it or not, there is so much more to learn on the topics we discussed in this chapter. Chapter 17 discusses trait objects, which are another way to use traits. There are also more complex scenarios involving lifetime annotations, that you will only need in very advanced scenarios. For those, you should read the Rust reference. But next, you learn how to write tests in Rust, so you can make sure your code is working the way it should. Okay. Tests is going to be a large topic. Okay. We are going to go over ownership inventory 3. Ownership in real world scenarios. Right, yep. So we're just back to ownership. They know. I think they know that nobody knows what ownership is. I think they know we have no idea what we're doing. And they're just peppering these things in. That has nothing to do with what we just did. I'm glad. Alright. Well, thank you so much for being here, Sorbet. Next time, we're gonna be doing the ownership inventory, and I am going to die. Oh god. I love that 2 times now. 2 separate times now. We've gotten some kid looking for Rust. Or I don't know if they're a kid, but some guy looking for Rust. And they find Rust. I'm very happy. Slowly we will indoctrinate the youth into our counterculture narrative. This will be fantastic. Anyway, once more, thank you, Sorbet, and thank you so much for leading me in the right direction. Several times there, I just wasn't thinking right, and I do appreciate you coming in to help me out there, help me out my understanding. Maeve came out with some funny things. New Rust propaganda. We will spread it by force. Right, thank you again,